seminar. Once in a while, we don't have a weekly seminar. Not because we couldn't find a speaker. Sometimes we do a break. But it's always great to hear some experts like David Lawrence. So we have David today. He's going to talk about OpenFMB. He'll explain what that is. But you also hear about the microgrid. That's another term that's coming into today's jargon. And Mount Holly, you may have heard, we actually did take a tour of Mount Holly not too long ago. So we'll hear those things. Let me introduce our speaker. He's actually, David Lawrence is an internationally recognized expert on the topics he's going to discuss today. He's a technology development manager with Duke Energy. He's working in the Emerging Technology Office. In this role, he provides leadership on a portfolio of technologies for the future grid, including development of use cases and requirements, architectures and designs, and technology test plans. He works in defining and executing technology evaluations and providing change management support. So Lawrence is currently focused on grid distributed autonomous functions, edge analytics, and security for distributed technologies. David has 38 years of experience in the energy industry. He works in research and development and IT management for electric metering, transformer, and switchgear product manufacturing. His roles included embedded systems and protocol development, engineering management, global engineering information systems, manufacturing, execution, and scheduling systems, product like management, IT management. So this is a whole career worth of things with his work. So obviously, a number of years, 38 years, gets you that sort of portfolio. He's a native of Portsmouth, Virginia. He got his bachelor's in computer science from Virginia Tech.
Woo-woo, the Hokies.
Let's welcome David.
All right, thank you. All right, so you guys can hear me okay, right? Yeah. All right, so by a show, I need to know who the audience is. Well, first off, thank you so much for having me come today and speak, because I think this topic is very important, and that, so by a show of hands, how many people here would consider themselves to be an OT person? You guys know what I mean, OT, operational technology? We have one, couple. I would say mechanical engineering, you guys are OT people. How many would consider themselves to be IT? Anybody IT here? More IT, all right. IT, what is it? Information technology. How about security? Any cyber people here? A few. I can snow you guys completely. What the heck? All right. Next time, let's get more. And then how about telecom? Anybody know anything about telecom? We have a few. Okay. Well, the key thing in all of this, and the point that I would like to make, is that, the grid of the future is we're seeing more and more distributed generation come. And there's lots of microgrids, and this is happening. We're moving more from a tree structure to more of a graph. And we'll get into the details of that. But this concept of bridging the skills between OT, IT, security, and telecom, it's really important. The way we connect and for all this stuff to come together, it's extremely important. So also, we're really fortunate to have a couple of Duke guys here in the back. We have Alex Vukajevich up here, who's a power systems engineer extreme. He's got more degrees than anybody out that I know, actually. And then we have Mike Grooms next to him. I'm not sure of Mike's background. But these guys, if you want to get some time and hang around with them, they're actually very good. And a few of these first slides here are jokes that Alex gave me in order to do today, just to sort of warm the group up. But one of our favorite conversations in Duke is this thing called these distributed autonomous functions. Anybody want to take a guess at what a distributed autonomous function is? Not really. How about a self-driving car? That could be a distributed autonomous function. The one that we really work on a lot is this concept of a microgrid, which would have solar, battery, maybe some CHP, some inertia machine, and it can run on its own. You can island and you can reconnect to the grid kind of thing. This is a microgrid. So we're focusing on what these distributed autonomous functions are. All right, so before I dive into what OpenFMB is and why we're doing it and security around it and these kinds of things, I'd like to mention that we are working on physical security. Duke is spending a small fortune. I won't tell you the number, but we're spending a fortune on upgrading substations and key assets all throughout the grid. And in some ways, it's kind of sad, you know, that you have to spend all this money on security and cyber because people are out there that want to break the stuff, right? But the consequences of breaking this stuff is great. There's a certain number of substations on the East Coast. If one of those disappeared or a couple of them disappeared, the whole East Coast could actually go down. So it's a serious issue. So we're hardening substations. We're spending a ton. The kinds of systems that you'll see, this is a checklist from a NERC program called SIP-14, where this is supposed to be filled in on the right, I guess, if you go out to a substation. I grabbed this slide because it has a list of all the things you could imagine that you would put into a substation, like fences, like smart fences, like audible sound sensors that don't listen to just somebody moving around in the bushes and then turn on the camera, but actually listens particularly for subsonic stuff off of a projectile, so it can know that that is a bullet or something coming toward the substation. We have a guy in our group that works on robots that would not be actuated until either a voice actuation, a sound wakes it up, and the robot can then move toward it, and then watch, and then turn the camera on, and then start streaming back to something, or collect local. So we're spending all this money on security. Physical security is important. So I wanted to lay it out there. And then just, it's up to Alex now. So 63% of you guys remember stories. And then 5% only remember statistics. The remaining, most of you are still working on your email. But it doesn't look like people are working on their email, so this slide is probably not very accurate. This came from Alex Dukievich, actually. So we're focused on the 5% that remember statistics. So this is going to be a brutal presentation. I'm not sure if you guys will be able to handle it. Too much to remember. So then, this is an interesting thing about the utility industry. So I did a career with Westinghouse ABB, metering, protection equipment, substations, distribution transformers, power transformers. I worked around all these boxes in the grid, right? And the systems that run them. The SCADA systems, these things that make the world go on the grid side, on the operations side. And as an ABB guy, as a Westinghouse ABB guy, I wanted to sell you as much product as I could possibly sell you. That's how I would become rich and famous. Like I am today, rich and famous, right? So on the utility side, though, it's a little bit different. It's much more of a not a capitalistic pig sort of environment. You know, it's much more socialism involved. We are in business to serve the community and provide electricity to everyone. So we do these programs like we ask our customers to use less at times. If we have a peak problem, we want you to use less. We also, yeah, what was that? Free light bulbs. Free light bulbs. We give away stuff. We give away LEDs. You know, LEDs in general can reduce your electric bill 30% across the board. So what the utility is seeing right now is a decline in revenues across the board. We also ask our customers, we'll pay you $50 a month if you'll let us take control of your hot water heater or your thermostat kind of things. So the business is a little different. And then we invest in equipment that we put on the feeder that actually reduces voltage and then reduces watts. And so when we do that, your bill is actually less. Why would we do these things? It's the cost to serve. To go out and acquire the funds to build a new plant and build something enormous, it's political. It takes a lot of work. There'll be a return on investment, but it has to be the right thing to do from a societal point of view. So this is the fundamental dilemma of being a utility. We are a regulated utility, and even the non-reg ones have a twinge of regulation to them. Unless it's just somebody out there peddling microgrids, which we'll talk about here in a little bit. All right, so I've been hanging around. In the last 2 years, I've been trying to become what I would call a hacker type guy, right? So I've got this tie on today and jeans, you know, and I'm trying to do slides with memes. My 16-year-old loves memes. And also the thing that's interesting going on is, have you ever been to DEF CON? Anybody been to DEF CON or Black Hat? It's a hackers fest in Las Vegas every summer. It lasts about 10 days. It is wild. You don't take your mobile phone in there, energized, because they'll have stations that spoof the mobile phone and will take over your phone. You just don't do that. You don't go with anything. You just wear clothes, no electronics when you attend this thing. But they always do lowercase. It's like E.E. Cummings. All the slides are on E.E. Cummings, and they show all kinds of wild stuff. So I would recommend all of you, if you really get interested in security, because the intricacy of security, I grew up as an embedded systems developer. Boards, chips on boards, write code, put code in chips, chips on boards, make all this stuff go. And it's fascinating writing at assembler and seeing what it takes to write an operating system and a linker and a loader and assemblers and compilers and how all this comes together. To be able to come in and realize all the mistakes that we've made. You can come in with a CGI script to a web server, completely bypass it, and get a shell script coming out to someone to say, hey, come on in and take over my machine. It's amazing, the intricacy of this stuff. So if anybody can get pumped up about it, we need your help. So come and join us. So happy Tuesday. And then the weekend's coming, so stay strong. Is that anybody? I want to see if I got a laugh out of that. All right, so this is my understanding of Duke. I've been with Duke 3 years in this R&D role. We're a group of 18 people, and we work a little bit on generation, not too much on transmission. We focus on distribution and on alternate generation forms. And the reason we focus on these things is because of where the world is headed with distributed generation, solar and wind and batteries. But my understanding of Duke, going back to 2007 or so, we started really doing this thing called smart grid. Now, I would argue that the devices are smart. Anybody want to offer what smart grid means? Quick definition. I'm not sure what the definition is. I'd like to know what you have in your mind when you think smart grid. What do you think?
A classical grid with some IoT data embedded on top of it.
That's it, exactly. That could also be connectivity. I'm not sure how smart it is. I would argue the grid's pretty dumb. The devices are smart, but I think we're yet to reach the place where the grid would really be called a smart grid. But this term has been used for quite a while now. So we started rolling out smart meter systems. We have these concepts. That one box up there is a node. That node is a collector to talk to all those meters. We rolled that out in Ohio. We use power line carrier. We use telecom cellular type connections. The slide on the right, the picture on the right are line post sensors. You can interrogate those. You see some solar. On the far right, on the bottom, there's community energy storage. Next to that transformer, that's connected in McAlpine to 5 homes, where you can keep the power alive on 5 homes for a curtailed section of the equipment in the home for a few hours. This is all experimentation kind of stuff. In that, you see big batteries, the thing that look like trailers. They're filled with batteries. It turns out a big battery, 1 to 4 megawatt type stuff or 250 kW type stuff, is really a trailer with an aisle down the middle filled with lots and lots of little batteries. Yeah, so you see CTs on a transformer and solar. So the point in this is we've connected it all. We've started to connect things. We run algorithms at a central site in order to try to optimize these resources. So that's kind of what the grid looks like. This comes from EPRI. Over on the left, you see generation. On the right, you see the consumers of the power. I would argue the world is really changing, though. It's moving away from this. This doesn't look like a tree, and it really doesn't really look like a graph to me. I don't really like that drawing, but we'll move on. So the problem with historically the way we built the systems has been to create silos. Now, you guys are new in your careers, and what you're going to run into if you go to work for corporate America or anywhere in civilization, you'll find that humankind likes to create silos. People kind of get together in a working entity, and they create a silo. You do something. The silos that you see up there would be, you have a system that runs SCADA, and it worries about the OT side of the world. And then you have another system that does metering. The metering world and the OT world, they kind of come together, but they really don't. There's a silo here. And also there's no data sideways in the field. If I want a meter to talk to a cat bank controller, to a voltage regulator, or to anything in the field, to an inverter, to a battery, to anything, they don't talk to each other sideways. They normally always go back up to a head-end system that sits behind the wall of the utility. The decisions are made centrally, and then a message comes back out somewhere. And those kinds of latencies take forever. You might be looking at 1 minute, 15 minutes, 1 day. In the case of metering, you might get 1 read a day off of a big collection of meters. Would you call that smart metering? I would call it really slow, stale metering. So we have this silo problem. Now, years ago, you see the enterprise service bus in the back over there. Years ago, people got tired of point-to-point where an application connects directly to data in this thing. So a company called TIPCO and others came up with a thing called an enterprise service bus, where you can publish information and then multiple applications can use that if they are destined to be consumers of that information. So the concept of an enterprise service bus is a great concept. It's a way to decouple. You want to decouple applications from data when possible. All right. So why is interoperability important? Well, we just touched on the microgrid, but there's a whole slew of distributed functions out there. This FLISR, this fault location, isolation, and service restoration, which is really self-healing grid. The grid can heal itself. That could be run not central, but completely decentralized. It does today. There are solutions for that, but the utility is slow to adopt them, mainly due to safety. People are afraid of whacking somebody. It is a big issue, and the systems have to be bulletproof from a reliability point of view. Let's see what else I have up there. The advanced demand response stuff can be done that way. Voltage management in general. Alex has worked on a power electronics piece where you can have meters in the field with a bunch of power electronics equipment that are helping with capacitance. If the voltage drops, you can lift the voltage. The voltage goes the other way, you can drop the voltage. This kind of thing. So these boxes in the field, data's going sideways, they're all working together. Yes? Oh, absolutely. I'm sorry. Please.
It's been a long time since I've been at electrical. How large is the microgrid?
The two that we built are, and some are, I've seen some as much as 2 megawatts of solar, personally, but the one that we built is 118 kW of solar, 250 kW of battery, 250 kWh, and a load of maybe 60 to 80 kW. So pretty small stuff. But what we've been doing in the one in Mount Holly has been working on the algorithms to optimize a small one, but then to be able to say disconnect. So it islands. And in the first one that we did, I'll get into this picture in just a second, okay? And we'll go through some detail on that. All right, so there's a lot of distributed functions that you'd like to have. The way to enable them is to do the work in the field rather than in the back office. We think you'll get more efficient and definitely more secure. It's kind of like if you have a big tree, and you have a head on it, you cut the head off, the whole system's dead. With a decentralized approach, if you lose one chunk of the graph, you can chop it off and the rest of it will keep functioning. Yes?
So when you say distributed, does that mean that each device is computing, or is it still some kind of a central within that microgrid?
In a microgrid, this collection of devices, they work together to pull off a function, which is to be the microgrid. There would be one, I don't want to call it a proxy, but one box would send status up to the big guy in the sky, because you need to be able to watch from a security operations center or a NOC, network operations center, understand what's going on with the grid. Because I say decentral doesn't mean that you're not connected at all and nobody has a view. You are connected, but you're really only feeding summary information up to the central. So the central has the view, but the central is not necessarily making the decision. That microgrid operates on its own.
So does the microgrid still have a centralized node?
When we get into the architecture of what we're proposing with publish and subscribe type protocols, that function could be distributed across all the boxes. Typically what you do, though, there would be one box in this collection that has the microgrid controller function in it. And he's the one that knows about optimizing, or she, excuse me. All right, so the back office, we spend a fortune doing integration in the back office, and what happens with silos over the years is that the cost of updating anything in a big monolithic back office system becomes more and more and more expensive. Yeah, so I like this point. The world has been, in my whole generation, I've worked on standards, but I would call them non-standard standards. There's DMP3, there's Modbus. Well, Wi-Fi has been a good one. Anything that falls in the commercial space has had a much better chance of living because so many eyes are on it and everybody needs it to work. But in the space of the energy sector, the individual suppliers of these protocols like DMP3 and Modbus and 61850, there is a standard, but they're all a little bit unique. This AMI mesh network stuff, right now there's a group out there called YSUN that's trying to clean up the last 20 years of what's going on in mesh networks. But we won't belabor that at this moment. But my point is that we don't have, their standards. The socket of a meter is pretty standard. You know, the 4 blades, that works. The socket in your house, that works. There's a different one for almost every country. Europe tends to have mainly 2, or they do have a ground, but not all countries, you know, so that varies. So it's a difficult thing to do. But I have a point on that. I think we make it more complicated than it is, and I think that vendors actually, I was a vendor most of my life, I think we actually make small changes to make it so when a customer buys our stuff, they have to continue to buy our stuff. A little harsh. All right, here's a, let me check the time, all right? Here's a beautiful day. Now, it's inverted because this is solar output coming off of solar, coming back toward the grid, which is why it's negative. This is coming off of our microgrid out in Mount Holly, where you see close to 100 kW coming back. Beautiful day. Now, I also have another beautiful day. Way up in the, high in the sky, there's some clouds. Not very many, they're kind of wispy. This is Cirrus flying by, but this is what the output of that solar inverter looks like. It's all over the place. So if you had a lot of solar, like 1.2 megawatts, what we have at the end of this feeder in Mount Holly, this thing is like a tail wagging the dog. It's moving all over the place. So you can swing voltage a lot, and then that has an impact on customers. So you really kind of want to clean this stuff up, you know? So how do you clean it up? We'll talk about that. Here's another view of it. One way to clean it up is to use a battery. So if you put a battery in conjunction with solar, then you can see the solar is going up and the battery is down. So they're working together in order to create a nice, smooth blue line of kW power output. So what I've learned from working at Duke and working in this lab and hanging around Alex and Mike is that I wouldn't deploy solar without a battery. At this point in my life, you know, I would do that. If I was to do this at home, I would make sure I had a Tesla power block or an in-phase battery of some kind. All right, so the reason I showed you this one function of this solar smoothing is because I'm going to give you an example of the central versus decentral. So in a central system, you see the fluctuation here happens in the solar. You pick up the fact that there was a swing, you communicate to a tower, it comes back to the cellular cloud, ends up at this head-end system off this line sensor. A company like Tollgrade or whatever has a head-end system that only reads their sensors in the field. That information comes back, it ends up in a decision-making block here, the decision gets made, and the response goes back out and says, hey, battery, work with me, you know? So this is really stale, really slow. Again, 1 minute, 15 minutes, once a day. This is not the way to focus on solving this problem. So the way to focus on it is, there again, there's the silo that you saw. We came up with we decided 3-4 years ago to take this enterprise service bus. This is open field message bus. We decided to take that enterprise service bus over there on the right and move it out to the field. And we call it the field message bus or the open field message bus. Now, all these boxes in the field, they don't have the protocols and they don't have the understanding how to connect to a bus. Not yet, anyway. We'd like for the industry to start adopting these concepts and put this technology in the end device. But today it doesn't exist. So you see the node up there. You can put all this kind of stuff in the nodes. So on the, we like to say south side and north side. Did I lose one already? Oh, good. Whew, all right. Thought he was leaving, excuse me. So on the south side, we speak an old legacy protocol. And on the north side, we massage the data, make it in a perfect format called the Common Information Model. On the north side, we publish it. So we have standardization when we put a node in. And also nodes can have applications like understand voltage management or demand response or different kinds of functions. Does that make sense to everybody? A little bit? No? Okay. All right, so then with the field message bus operating here, the same example, you have a disturbance in solar. The node picks it up in the field. The node turns around, talks to the battery, you know? I mean, duh, brain did simple, right? Managing all this. And then you still report on the fact that there was a change of state. You can report back up to the top.
I just had a question. Why does it take so long for it to go to the central station?
That's a good question.
Today we work with YouTube, cloud services, so latencies are far lower, right? So is there anything special?
It's a good question.
I
think there's two issues. The number one issue is the communication connection. So in your home, you're looking at 50 megabits, right, through cable modem, or something like 50 megabits, or soon with fiber in your neighborhood with AT&T and Google, you're looking at 300 megabits. This is what you got, right? So this AMI meter that you have on your house, for example, let's take a meter with a mesh network. So there's a collector somewhere on a pole that talks to some number of meters. That collector is connected with cellular, and the meter is actually talking about 150 characters per second. The design criteria for that device was to reach that last mile as cheap as possible. Now, there is a city called Chattanooga in Tennessee where the municipality owns they provide cable, they provide the full infrastructure, and they're the only ones I know of that have fiber everywhere. It's a small town, they have fiber everywhere. So you can have a service where I could potentially run this kind of application centrally based, also if it's small. There is another problem though in the back office, is that the back office becomes more and more convoluted. You want to break your problem down. I would argue that I want to break it down if it makes sense and distribute it anyway and report on the results rather than, you can't, if I try to control every person in this room, I can't control all you guys, right? It's not scalable. And then I add another room and another room and another room, and I'm the guy that has to manage each individual box. I really want to chunk it up into pieces and have you manage, that group in the top up there, you guys manage yourself. Tell me how you did. You know, this is why we break into groups. This is why you have platoons in the Army, you know, these sort of things. It's scalable. Yes.
But also related to the distribution network, what's the dominant hardware communication layer that's responsible?
Depends on the utility. For example, SDG&E runs fiber to all the substations, and they run a lot of microwave. It's because in SDG&E, where they are in San Diego, they have line of sight like crazy. In North Carolina, we try to run 900 megahertz in some places, but anywhere you have a lot of pine trees, that's not very good. Duke in general has 280,000 miles of line across 6 territories. I should have put a slide in here about how big Duke is. We're like 50 gigawatts of generation, 280,000 miles of line, 2,300 substations. It's mainly cellular. And cellular latencies tend to run between, if you get private cellular, which is what Duke does for the most part, even though you wonder if it's really, you know, is it really, what does that mean, private and public? But it's private, you know, AT&T or Verizon carves off a piece for us. The latencies are 100, 150 millisecond type things, you know. If it's public IP addresses on cellular, it's more 200, 250, and it depends on your coverage and where the towers are. So that's the reason that the latencies. Now, if you had, and also the convoluted back office, you know, I mean, you wouldn't imagine how many head-end systems there are in a utility. And the way security works is you run a VPN session from all these, a VPN for every point that you have to talk to, you know. This becomes, you know, just brutal from a management point of view. All right, so just real quick, I'm going to go a little bit faster, I think. Going back a few years ago, we decided to take this field message bus concept, and we worked with 6 vendors, and we went to Distributech in 2014, and we did a voltage management application with a capacitor, with a cat bank controller. And we pulled that off. And Mike Groom is one of the guys that made that happen. And where was that one? It was in San Diego? Yeah. And then a little bit more focus here on the concept of the node. I'd like to drill into it just for a second. Back to the node. The node, it supports this concept of, you know, the utility, we buy hardware and we put it in the field and we get a return on investment on it. This hardware has to live. The electronics has to live basically, I think it's 12 years. Transformers, big power transformers that cost a couple $1 million, they live 30 years, 40 years, and these sort of things. So it's a depreciation schedule involved in this. So you can't rip and replace anything. You don't just say, I don't like that system anymore like you do with your cell phone. You know, you throw the thing out in 3 years and you get another one, right? It doesn't work here. So one concept of a node is to put a node in play, and on the south side, it handles legacy protocols. You see C12 up there? That's an ANSI protocol for metering. DMP3 has been around for a while. Modbus in the IEC world is 61850. Those are the classic legacy protocols that exist in our space. So the node speaks that on the south side. On the north side, it speaks these new IoT protocols, like AMQP, the Advanced Message Queuing Protocol that came out of JP Morgan, out of the financial group. The Message Queuing Telemetry Transport Program, MQTT protocol, came out of IBM. This DDS thing came out of the U.S. Navy. The Navy is running their weapons systems on all the battleships with DDS, which is data definition services, data distribution services. So again, you know, handle the old world, and go to a new world on the north side, and at the same time add functions and add security to it. These old boxes don't have security built in. It's just not there. All right, so then in 2015, we took these concepts around Open Field Message Bus, and we said we want to create a standard based on this reference architecture. All it is it says, don't create anything from scratch, have a best practice standard. And we got it standardized through this organization called NASB, the North American Electric Standards Board. And it says, start with the business case, understand the use case. How many of you guys here have done UML? Anybody done UML? You guys aren't? We have a few. Good, all right. UML is the schematic, the hardware schematic for software engineers. You define the actors, you define the messages, you do sequence diagrams. And the whole purpose in this is to understand the message sequences and what is the data that needs to flow across all of you guys, you know. So we got that as a standard. It's a reference architecture. So what is it not? It's not a new protocol. It is not a new data model. It uses the Common Information Model, and it uses 61850 data structures, things that already exist. It says take the best of what is out there and use it. And it's definitely not that. There was a poll to figure out what the graphic needed to be for Open Field Message Bus, and somehow this Fox thing won. And then we had guys running around at some of our meetings wearing these Fox things. But that is not the Open Field Message Bus. That's a logo for the Open Field Message Bus. A little bit about the microgrid in Mount Holly. This is an older picture of it. In the top right, that's where the 118 kW of solar is. There's an islanding switch. There's more PV here on the left for a solar carport. And then we have the load in the building. This was a lab that Duke had that's been used to service a lot of the generation facilities. I think the place was built in the 1970s. If you come out to Mount Holly, you guys are all welcome to come out. Maybe some of you have had a tour there, but come out and visit and we'll give you a tour. But it was going to be closed up or decommissioned. And then our group, this Emerging Technology Office, we have put some money into it and are bringing this lab back and doing a lot of development out there. So then here's a picture of the switch yard, and you see this battery, and there's a secondary cabinet and all the pieces, the PCC. And then just a little bit more about the Open Field Message Bus. I like this point because, you know, if you look around at the devices in the grid, and you go, boy, that looks like a complicated device. Yeah, it's got complexity to it. But if I want information to be shared across, I want you 5 guys in that row over there that are mechanical engineers, I want you to share information to solve a problem in the grid. In order to do that, you need an A to D converter, and you need to be able to read voltage and current and the phase angle between voltage and current on 3 phases. And from that, you can derive watts, VARs, and VA. And I need you to have accurate time. So you guys timestamp this stuff. And if you each have a different function, you can just share that kind of content across each other. And that's all you need. Now, if you want to do some deep study into waveform capture, pull harmonics out, you need more. But the basic function of the electrical grid revolves around these kind of quantities. You also see state of charge up there for a battery, and then the kind of actions you take that you might tell that guy to trip, which means open. You might tell him to close. That's the extent of the complexity of the control mechanism, you know, that exists in the space. It's just there's so much of it. But that's it. So why is it, after all these years, is it so difficult for us to standardize on a data model with those names and have people agree on that? We still don't have that today. 61850 has a model, and we could use that, but that's a different story. So anyway, I don't want to belabor that point. But the point is that at the lowest level here on this microgrid where everybody's connected to the bus and they're sharing information, that's all the data that is shared across these guys. And this thing called a microgrid optimizer, he understands that when the point of common coupling, the grid-connected piece, opens, the battery has to become the voltage source for the grid and the frequency source for the grid. So the battery takes over. He needs a message in 60 milliseconds or so. That happens, and he takes over. When you go to reconnect back to the grid, you have to marry voltage, you have to marry frequency and phase angle back, and then you can close the grid. And the microgrid that we built in Mount Holly, you can seamlessly island and seamlessly reconnect without having the lights go out. And then now we're going to finally start touching on security here halfway through this thing. All right. So security. From doing a lot of different projects, we realize people have intrusion detection systems. The point in this security angel is that it watches the packets and understands what's going on with the protocols, but it could also understand something about the single line diagram in this thing and understand something about the electrical circuit. to tell you if my microgrid is being spoofed. So we're looking at how do you add that kind of functionality into these things. So then again, so when you guys leave and you go home and you talk about publish and subscribe protocols, again, you guys are all working together, you mechanical guys here, right? And you publish every 5 seconds, and maybe you publish every minute, and you subscribe to his stuff, and you subscribe. You guys all just work together with comms, right, and make it go. In the history of the world, the SCADA system goes, what do you got? 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 And polls all day long, round robin. And then if you ever do banking with the bank, right, I'm the server and you're the client, you do HTTPS, secure hopefully and not HTTP, you connect to me and you go, I want a page, and I deliver you a page. That's client server, get put, and there's polling, which is what we do a lot of in the SCADA world, and there's publish and subscribe. Publish and subscribe. You solve the problem, you understand the use case, you publish at a rate, you publish at a rate, you publish at a different rate. Those that need to subscribe to the data subscribe. So just keep that in your head for the rest of your career, the next 40 years, and chase down publish and subscribe protocols. All right, here's a single line diagram from the microgrid in Mount Holly, just to show it to you. And then in this effort, we worked with 27 different vendors to try to get this point across, and we pulled this off, and in 2016, we did this elaborate demonstration at Distributech where we had 12 booths, everybody all interconnected with cellular and 900 megahertz, doing publish and subscribe across everything, PubSub with common information packets, the simple packets that I described, moving these things around. Yep.
When something is published, is that published information distributed across the system so that it can be accessed from anywhere synchronously?
Well, the simplest is, so one protocol, the DDS protocol, the data distribution services, has maybe 26 qualities of service. If you use UDP, then it's a broadcast, essentially, that everyone subscribes to that needs it, right? So they all would hear, and only those that need it would pull it in, right? That's a broadcast style. That would only work on the LAN. You don't do that across subnets, right? So then another approach of a quality of service is, even though it's a publish, it's really a writer to a reader to a reader to a reader. So it looks like PubSub, but of course I have to send it to your IP address and to you, right? So there's a lot of different flavors of that. And you definitely wouldn't want to broadcast from inside of the microgrid. I'm going to show you some system within system stuff. You wouldn't want it to go all the way to the top unless, that doesn't make sense. The proxy for the microgrid would publish up to the next level. But you wouldn't want all these guys in the microgrid, their traffic to be heard above you. Okay, unless there was an application, like let's say there's an asset health application. And we'd have to devise what is the architecture for that, right? I got one guy that's feeling really sick, and you want some system somewhere to know that that guy is sick, right? Does it go to the microgrid controller? Does it stay local? You know, where does it go? We're wrestling through these architecture issues. That's a good question. All right. Yeah, so let's see. This is the view of the world that we have today from a security point of view. You've got a SCADA system, supervisory control and data acquisition system at the top of the world, and it polls the gateways. Tier 2 is a substation, and within that you have maybe protection devices. The top polls. I go, what's going on, what's going on, what's going on all day long. Tier 2 polls Tier 3. If you reduce security on this, and what we do today is we run VPN. We do encryption between Tier 1 and Tier 2. We hide it. We obfuscate it. We do it with a VPN or whatever, layer 4, layer 3 in the OSI model. You guys are going to all go get mechanical engineers. You're going to be diving into the OSI model. As soon as this is over, I can tell. You're going to be enthused about it. So anyway, essentially you're putting a fence. You put a fence around everything from an IT point of view. Another way to do it that I've seen in architecture to pull off the self-healing grid, I've seen substations at Tier 2 want to talk to each other because there's a concept of a tie point. But we don't have to go into that. This is another structure, All right, so now let's start doing some hacking. This came out of memes with, so Bob the Builder's not here today. I'm Daisy the Destroyer. Boy, that went over, didn't really go over well. Alex, can you tell that joke better? All right. So going back a couple of years ago, we did a DNP3 hack. Now we're totally into cyber now in our lab, where we had one of those original architectures. You have a SCADA system on top, polling over on the left. It's polling a rack over on the right. And in that rack is a gateway, which is Tier 2, and below that is Tier 3, protection relays and other equipment. Tier 2 polls Tier 3. We broke into the substation. We climbed the pole. We cut the lock. We'd already socially engineered the key to the internal room. We went in the internal room. We found an available switch or a hub, and we took a Raspberry Pi that we'd already preloaded with some code, and we plugged it into that switch, and then we left. Oops. When we left, we stole some copper and didn't kill ourselves, and we made it look like a copper theft. But we left a Raspberry Pi energized, installed in the equipment. Now what the Raspberry Pi did was, it was downloaded with 3 pieces of software. It had OpenDNP3, ARP spoof, and Suricata. So it started watching the network traffic, watched all the traffic, and very quickly could tell who the master slaves are. And you can use a TTAP if it's a switch, or if it's a hub, you see all the traffic. There should never be a mirrored port off of in a substation. So anyway, you watch the traffic, you see who the master is, you see who the outstations are. Within 500 milliseconds, you know the architecture of the substation. At that point, you can take over with an ARP spoof, you take over the identity of the gateway, and you just start blasting random binary outputs to the tier 3 devices, which are protection relays, which control the breakers, which control their fuses for a line segment or a feeder that's got 5,000 homes on it. So you start yanking the power on all these homes. On, off, on, off, on, off. You can do it really fast to burn up a lot of equipment, just get some weird frequency going, and then return the line back to normal state and go to sleep, wake up and do it again in 30 days. So that's one hack that we did in the lab. Now the reason we did this in the lab was to prove the DNP3. We already knew from working with these guys, Sistrunk and Crane, the DNP3 was hackable, but we wanted to see it ourselves. So we made this happen working with a company called Viasat, who is, they're big in the security space. So back to a little bit of top-down stuff. When you're, if you're use case focused, then you look at use cases from a security point of view. The number one use case to pull off for a new product going to the field is how do you provision that product before you take it to the field. Because when you get into security, you're going to find this PKI, there's all these keys, there's encryption, there's identity, there's integrity, there's trust, there's all this stuff that you have to do that doesn't exist today, which is why DNP3 is a wide open, clear text protocol, which is why we, from the central site out to the substation, we encrypt. We VPN tunnel it, we do a layer 3, 4 thing, nobody can see it, you can't get it, but once you're in the substation. Have you guys ever heard about a lot of systems in the world are hard on the outside but really soft on the inside? I would argue that the majority of systems that exist in the world are kind of like that. So if you can get into the system and plug in, it's yours. It's much harder to sit on the outside and pound on firewalls and try to get in. It's possible, it happens all the time, because people don't do firewall rules as good as they, whatever. So, but anyway, the idea around this is work through the use cases. These are key topics for, they're called industrial control systems, is the space I'm describing, these SCADA systems. In this space, these are some key things, the whitelisting, you should know every device that's out there. There should never be somebody join the network. It's not like on the corporate side. The corporate side, you have visitors coming and going all the time. People are showing up, new boxes show up, laptops show up. On our side, there are no laptops, really. You should know every device that's out there and enforce that. So that's the whitelisting piece. So a lot of security nomenclature here. When we were putting this standard together, we wrote a lot of requirements. This is just something that you guys can take with you if you're interested in looking up the requirements. And then we also referenced, there's a ton of documents out there on requirements for security in our space. The thing that I find mind-boggling around this is that if you go from NIST to NERC CIP to IEC to IEEE, and you read what the security standards are that each body has come with, they all say the same thing. It's kind of rude. They all say the same thing, but there's little or no best practices out there that have been implemented other than this. So then one of the protocols we worked with is message queuing telemetry transport protocol. It's got username and password at the top level. It's another publish and subscribe one from IBM. If you get into the OSI model and you study what's happening at layer 4, you'll see that you can encrypt at that level, and also you can manage certificates and stuff. So here's what we had to do in the microgrid, in the lab. We had to automatically generate our own certificates, be our own certificate authority, not global sign or somebody, use our own authority. We had to generate a certificate. We had to manually deploy the certificates to put them on the machines. We had to manage all the keys and make all this stuff happen. And what you realize then is you can have a secure environment, but then to manage it is completely painful. It's horrible. That's one step. Then the next one we worked with, the best one that I've seen from a control system point of view, is this data distribution services, this DDS thing that the U.S. Navy used. We stole it from the Navy. It's been around like 20 years, 15 years or so. It does, if you're into crypto, it does an asymmetric handshake. When everything comes up, it negotiates all the whitelisting, all the flows, who can talk to who. It uses certificates and asymmetric keys to get everything set, and then you have topics. You have these publish and subscribe topics. You publish a topic and you subscribe to topics. The readers and writers of the topics are actually secured with a symmetric key in between each individual. So when the thing comes up, there's this mass activity that happens where all the key information gets securely shared across all the devices, at least the first time. They're all up, and then they all rock and roll in a secure manner. But I know of no other system in the world today that operates like this, at least not yet. I'm sure there's a few others, but so it's a tough problem. So I'm trying to give you the feeling that security is a tough problem to pull off. We're getting, still going. I should have asked more questions, but go ahead.
Yeah, is there enough compute overhead to this? Are you using specialized processors for all the crypto part of it?
Well, if you look at a node could be basically kind of a Linux box. It doesn't have to be a Wind River box. A node would normally have a couple of cores. If you look at the SCL gateways, they have a couple of cores in them. One would be for security one. Let me hop into this and we'll go into where we're headed is even deeper architecture into what the boxes need to look like. All right, so then, best practice security, reliability, determinism. PubSub gives you, because you've solved the problem, you understand it, you're not polling as fast as you can, PubSub gives you a level of determinism. Whitelisting, I mentioned that. You want to understand the flows between me and you and me and you. These are valid, but for me to talk to you, that doesn't exist. It should be configured that I would never even try to talk to you. If I ever tried to talk to you, it's bad in a control system. It doesn't happen. It looks like best practice in the world today is this concept of PKIs and certificates, public key infrastructure management. We're going to have to go that way. ABAC is actually attribute-based access control. Everybody's heard of role-based access control based on who you are and your login and all that. You can do certain things, but this is the world security. Everything needs to be logged. We spend a fortune doing this NERC-CIP stuff, which is a way of reporting to our national organizations that we're doing the right thing from a process point of view and that we're secure. But we really don't have a good way to generate that information. We're proposing that the actual boxes that do the logging of everything that happens on an endpoint to gateways to all these boxes actually creates logs that help you get to NERC-CIP compliance and can be used almost as reports in this thing. Very powerful concept. And then when you look at how do I manage all this stuff, this is the nightmare. It's the configuration management of a couple of million meters and devices all over the place. It wouldn't be so bad if we had high bandwidth. It would be easier, but we have pretty constrained type systems out there. And so how do you handle legacy? Where's the world going? The whole trade-off between it. We try not to. I'll give an example of an AMI system that I know of, a metering system that has maybe a few, I don't know how many exactly, probably tens of thousands. In order to do a patch across those with the speed of the networks, 4 months, this kind of thing. So to me, that's not doable. That's unacceptable. So there's a lot of change going on in our space. So you have all this renewables and distributed generation stuff happening at the same time the networks are improving. It's a fascinating place to be at this point in time. System-wide visualization, case tracking. The real thing that we're doing in our group is we're trying to discover what does the procurement language look like, meaning when you work with a vendor, we need to tell them what we like. And historically, the vendors have told us what we would like in a lot of ways from some of these products. Not always, but quite a bit. So we're trying to turn that around through this R&D effort and understand what should this, the vendors know from an OT point of view what that box has to do. But from a security point of view and from an IT configuration point of view, they're really great at OT, but they might not be so good at IT, So all these worlds are coming together. So there's two things going on in the world. There's one group that says put a fence around everything and just leave it at that. And the lower levels in the Purdue model, there's a thing out there in the manufacturing space, you guys can look this up, called the Purdue model, from layer 2, 1, 0 down. We're not touching the boxes, because if you do, you're going to break the timing. But I don't believe this. And then there's another world that says, yeah, we're going to put fences around everything, and we're going to have defense in depth and make it secure. But at the same time, yes, we are going to do PKI and certificates. Now, the certificates that come out of X.509 world, out of HTTP, out of banking and all this, are too fat. They're too fat for the networks that we run. So there's an effort going on right now to come with a slimmed down certs and slimmed down security algorithms. Most are using elliptical curve Diffie-Hellman stuff because it's the tightest one that we know of today. All right, so those are the two big battles. What we built in Mount Holly is you see the normal classic structure there, and then on the bottom right you see a bus structure. So that's the microgrid. And then where we're really headed is this next year. What we're working on is there's a system over there on the bottom right. That's the microgrid. And you see the green one. The green one is the one point that talks to the system above. The system above that, in this case, happens to be one feeder on a substation. So we have a system within a subsystem. And then the green guy on the top up there would talk to a system above it, if there was a system above it. I would argue that this model could represent the whole structure of the grid across the United States, across the world. Why not, you know? All right. So here's a new picture that Alex took with a drone. If you want to talk about drones, Alex is a drone expert. You're not a drone flyer, but he knows all about drones and the legal aspects of drones and their capabilities. He took this picture with his drone pilot, and you see there's solar up there in the top right, and we've added a new battery, and we're getting ready to recommission a new microgrid that has a new behavior around how microgrid should work. All right, and so then on the bottom right here, that's the microgrid. That's a system, and then that's within a system of the feeder above it. You can't hardly see it probably, but everywhere you see a little thing that looks like what does it look like? Well, that's an antenna. You see these little antenna things sticking up. What we're getting ready to do as an experiment to see what the future is going to look like is we're going to optimize this Rankin feeder, this feeder, that happens to have a microgrid on the inside of it. The only place we'll talk to that microgrid is at that point of common coupling. I'll come to you, you're the microgrid, and I'll go, you know, looking at what's going on with the 1.2 megawatts of solar at the gypsum factory down at the end and what the load is for today and the sun's shining and the lines moving all around, I'd like you to do this for the next 5 minutes. Can you do it? I want you to manage watts or bars or manage voltage or manage frequency. And I give you a schedule and I give it to you and you tell me whether you can do it or not, and then I leave you alone for the next minute or 5 minutes or 15 minutes or whatever. So we're trying to do a system, only focus on the interface. I don't worry about the stuff on the inside, only the interface. And then the system above that, same deal. Until you go, I don't know how many layers up you have to go exactly. I don't think there's any more than one more above it. All right, so then, let's see. These are the key things that we're doing this next year. We have a group inside of Duke that are hackers that will come out to our lab and start really whacking on the stuff. We have that going, and it's unbelievable what they can do. But they've never really taken on the OT side, the control system side. They've been, all these security guys in our space are all in the corporate side of the business, worried about the internet-facing stuff, the firewalls, you know, the Duke Energy portal and Maximo and all these different systems, you know. But we haven't done the focus as a sector on the control system side, which is where we're headed now. Yeah, so anyway, this is really in the weeds. You know, you have to be able to put identity on a board, and that identity cannot be changed. The two ways to do it today are this trusted platform module or with a puff kind of thing. And we can dive into the technology around that. All those are fascinating. On a box, the world today, you can have multiple cores doing things in parallel. And the Linux world has a concept of containers, where you could have security in one container. You could have the main function of that thing in another container, the communications in another. All this in one small box. It's coming down to chips that are like nothing, you know. It's getting very small. But the concept of containers has to be adopted in our industry as we move forward with bringing the IT to the OT side. Yeah, so the things that we don't do today are typically, if you want to run an application, it needs a digital signature. We're going to continue benchmarking, and we're trying to build, Alex is working on a digital substation. We could talk about what that means in another session, but we're working on a digital microgrid. Today, everything's still a mix of analog and digital. Time synchronization is key. Anybody working on the PMU stuff? As you dive deeper into that, yeah. As you dive deeper into that, you'll understand the importance of time synchronization because GPS spoofing is a big deal right now. I know of 2 projects going on, one with EPRI and one at SDG&E and with Southwest Research Institute, where they're looking at GPS spoofing, and they on a minuscule waveform into this RF receiver, they very, very slowly over a long period of time modify the time in the GPS receiver. And at that point, you know, you can have the grid can actually collapse depending on where these points are. You know, so it's this crazy stuff going on. The behavior analytics I already talked a lot about. Signing of messages, and then the thing that can really, this is a tough one, you know, the utility in general is not really willing to go to the cloud unless we get our own cloud, but the savings and to be able to have a trusted cloud, the savings around this are enormous based on how much money we spend in IT and if we could outsource it to a cloud provider. I think the cloud's the future for sure. But you have to have a lot of different trust and service level agreements between different vendors to make that go. All right, and then just a brief point back to the lightweight crypto. In California, SDGE, Lawrence Livermore Lab, different guys are working on what is this lightweight crypto? What does it look like? How do I do it? What does a lightweight certificate look like? And they're working on a standard, and they're hoping to take that. They're working on these pieces, and they're going to take that into the to get somebody like Oasis or the IEEE or IEC to pick this up as a standard. They're going to try to get it done in 2017. All right, so, you know, the one thing that I've liked about the 38 years I've been blessed to be in this world and to be able to do this kind of work is that it really is fascinating, and it takes a mix. You got to have mechanical guys, you know. You got to have all the CAD. You have to have all the product lifecycle management systems. You have to have the guys that run factories and do design, you know. You got to have all those skills. You got to have the OT guys, the guys that understand power electronics is the new thing that's coming. Power electronics is going to obfuscate and get rid of all these transformers you see on poles, these oil-filled things. Hopefully one day they just completely disappear, and it's going to be you guys here that are going to make that happen. That's happening. You're going to see DC to the home. Maybe that socket on the wall over there changes. Instead of being this thing, there'll be something on the top that's a 24-volt DC. Get rid of all those wall warts that you have all over the place in the house. Those disappear. I've seen smart breakers that have revenue-grade metering built into the breaker box. You know, maybe the meter disappears. DC to the home, a beautiful 120 to the home, if you still need 120, or 240, beautiful, no harmonics, clean as all get out. A lot of the problems that the utility has to address today with equipment that they put on the line and studies and all this kind of stuff that we have to do to make sure that power quality is right, boom, goes away with the power electronics. Now that doesn't mean that there won't be other problems that come with it, but you know, humankind's moving forward. So the power electronics, the mechanical engineering stuff, I mean, the IT, the OT, the security, and for me in my career, the thing that we've made so many decisions based on bad telecommunications or not having that 300 megabits that you would like to have. If I have that really changes things a lot. You know, you need to keep it going. I've often wondered why utilities haven't been faster to try to get a small sliver of the bandwidth of, you know, Time Warner cable. We could put a box outside and connect in with that and tie the meter to that, you know, and in urban areas, run everything that way. But I have never gotten an answer yet as to why we haven't done that. But that's happening right now. There's a project happening with EPRI that I know of where they're saying when you go out and you buy a router to put in your house, that router has 2 SSIDs in it, one that you manage and one that the utility, if you agreed, they manage that. You can't touch it. You can't change the password on it. You know, one of the problems with being on the homeowner's network is that they change everything and then you expect it to work as a utility and it doesn't work, you know. So that's one approach that I've seen to make this kind of thing work. The utility has to decide what business we're going to be in. Are we going to manage distributed generation? Picture thousands of DG points all over the place instead of one big plant down the road with smokestacks. Tons of DG, community solar, community storage, all over the place, all intertwined, all working together, you know. What business are we going to be in? Are we going to manage this stuff? Are we going to push it? So, you know, there's kind of a transition period happening. What's going on? So it's a fascinating time to be in the space. I'm right at time, I think, if I can see it. So, I didn't mean to bore anybody, but any questions? Get enthused, man.
Time for a few questions.
So, I mean, do you have a simulator that you use to study all of this? I mean, these are system problems.
You have to simulate everything before you do it in the field, and we're doing it with you guys. This is UNC Charlotte.
I see.
You guys have connection into our lab.
Including the security issues and all that.
Well, I think security is kind of a big unknown for everybody. I don't know, when you say that, I don't know what I would add to the simulation to say, yes, I prove that it's secure.
Other simulated attack, like the one you did physically. At this point, I'm just wondering.
Probably, from a simulation point of view, from an OT point of view, let's take Alex's drone and fly over a substation and drop a chain across a power transformer. So the simulation would say, short circuit power transformer. Boom, what happens? What happens, Alex? It blows up. It launches off the pad, right? It's going to take, the sad part is the backlog on these and the engineering on this is 6 months to a year. You know, and these aren't the kind of things you keep in inventory, you know, so that's kind of.
In the slides of the area of the investigation, I didn't say about wireless security. Actually, they do wireless sensor. If I have some jammer to, like, you cannot transmit anything using your wireless sensor, then you have problem with your control, right? So do you consider this kind of security in the smart grid?
I think that's a horrible thing to have happen. I agree. We're aware of it. I don't have it on the list. We're kind of dependent on EPRI, the Electric Power Research Institute, kind of chases those things. Also, the national labs. Oak Ridge has a strong security program, as does Lawrence Livermore and others. So I agree. But our group is not necessarily focused on an RF attack or an EMP kind of thing, or no.
One final question.
Will you expect the microgrids to be EMP protected?
Wow. Well, it means putting, my understanding of it today means putting a Faraday cage across it. And I would say from a cost point of view, no. Does that mean we're vulnerable? Yes. But that's almost a business question. You know? Or maybe we have to have one event, and then we'll do something.
It's coming.
I hope not.
Also, you have fiber in your SkyWire. Why don't you build your own communication system?
Fiber in our SkyWire. I don't know SkyWire. Where do we have SkyWire?
The wire on top of the transmission system.
Oh.
That's not fiber. That is the communications between the transmission substation that has to trip really fast. So the fault because condition relays cannot trip fast. So typically they have it's not a fiber wire.
So it's copper?
Yeah, it's copper.
Or twisted pair?